Hello, my name is Kylie Cooper, and this is my Engineering 1080 project for statics, teaching a statics problem. So I actually decided to go with a beam and pin problem for this, and I chose it mostly because at my internship, I see a lot of this type of statics problem with inventory shelves that we use. And so when we're using forklifts to put pallets onto these inventory shelves, it reminds me a lot of this beam problem where you're adding a force downwards and towards the beam, and it's being supported on two sides, similar to these inventory shelves that we hold our pallets on. So yes, I gained a lot of inspiration from my internship at Minnetronics Medical as an industrial engineering intern. So my problem statement that I have here is to determine the horizontal and vertical components of the reactions on the inventory storage shelf at Minnetronics Medical caused by the pin at B and the rocker at A. Neglect the weight of the shelf. So I have the rocker at A and the pin at B, and I have all of the forces stated here as well as the length of the shelf and the thickness of the shelf so that we can solve for each of the horizontal and vertical components. So my game plan for teaching you how to solve this statics problem is to begin by drawing my free body diagram, and then we're going to analyze each support and determine which type of components we can break those supports into, X and Y, or just X or just Y. And then we're going to set up the equations and then solve for those unknowns in order to solve the problem. So my first step was to draw the free body diagram, and so I just kind of took a picture of my work because I wasn't sure how else to show it, but basically what I have done here is I've taken those supports out of the equation and I've compartmentalized each of those supports into their respective X and Y components. And then I also took the downwards force at a 45-degree angle and split that into the X and Y components as well, with 500 cosine 45 degrees and 500 sine 45 degrees shown right here. And we have those same dimensions, 7 feet by 0.5 feet thickness. And we have those same downward forces acting on the B pin and in the middle of the beam. So step 2, we're going to analyze those supports. As I had said before, there's a rocker and a pin, and rocker A, we actually won't have any X component that we're solving for in this because with a rocker, it's held up just in the upwards direction. It's not able to move side to side in the X direction. But the pin at B gives us X and Y components because this pin is able to kind of move around a little bit in the X and the Y direction. So we can solve for both of those using our equations. So these equilibrium equations, we are going to be using 3. We're going to be using the sum of the forces in the X direction equals 0, the sum of the forces in the Y direction equals 0, and the sum of the moments at B equals 0. So we could solve it using the moments at A, but I chose to use the moments at B because that's where the X and Y components both are. So that has the most forces, which means that solving for the moment at B is probably going to be the easiest route to take in order to solve for all of those unknowns. And so my last step is going to be solving for those forces. And so how I did this was I took the sum of the forces in the X direction equals 0, and I plugged in that downwards and diagonal X force, which was 500 cosine 45 degrees, and that was in the positive direction to the right. And then I subtracted the X component of that B pin, and those are both equal to 0. So as you can see, you can easily solve for BX here, which I got to be 353.5 newtons. And then using this, we can go down and solve for the moments at B. So this one's a little trickier because we are multiplying the force times the distance of each component of the whole entire shelf. So 100 newtons times 2 meters is that first downwards force. From the B direction, it's only 2 meters, but if you were going from A, it would be 5. So on, we kept doing that the whole way, and the only unknown in this equation is AY times 7 meters. And that's 7 meters because AY is at the opposite end of the B pin. So AY is going to be the entire length of the shelf times the unknown AY. And so we set all of these different components equal to 0, and the only unknown is AY. So we can easily solve for AY, which I got to be 255.9 newtons. And then for my last equilibrium equation, I have the sum of forces in the y direction equals 0. And for this one, I'm solving for the y component of B, which we still have as an unknown force. And for that, I took all of the y direction components, which are that AY component that we had just solved for, which I had plugged into this equation. So 255.9 newtons. And that is only upwards force. The rest of them are going to be working downwards, so we're going to be subtracting them. As I put here, we have our positive direction upwards, so all the ones downwards are going to be subtracted from the positive. So I have minus 500 sine 45 degrees from that downward angled force that I showed you in the beginning, minus 100 newtons, which is in the middle of the beam, minus 300 newtons, which is at the end of the beam on pin B, and then plus BY, because BY is going to be acting in the upwards direction, so we're adding it. And that's all equal to 0. And then so you're going to solve all of that for BY, which I got to be 497.7 newtons. So that's how I solved this equation, or this problem. Again, I took a lot of inspiration from my work at Minitronics Medical. I also used the book a little bit in order to kind of get an idea of a good equation that I understood well enough to be able to teach it to someone else and that also related to my life. And like I said, seeing these inventory shelves in everyday life gave me a lot of inspiration, and seeing it every single day, I felt really comfortable being able to teach it somewhat to someone. So yeah, that's how I would solve this problem. Thank you for watching. Yeah.